My dear students, welcome back to our channel. In this video, I will be explaining the BSc first semester subject Chemistry as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is: explain Fajan's rule with examples. Fajan's rule. Fajan's rule helps us predict whether an ionic bond will have more covalent character. It says that a bond becomes more covalent if 1. Cation is small and highly charged, small size higher polarizing power. 2. Anion is large and easily polarizable, large size easily distorted electron cloud. Why it happens? The positive cation pulls the electron cloud of the anion toward itself, causing sharing of electrons. Covalent character increases. Example: Li lithium ion, Li, is very small, iodide, I, is large. The bond shows more covalent character. NaF sodium ion, Na, is larger, fluoride, F, is small, bond remains mostly ionic. Tip to remember: small cation plus large anion is equal to covalent character. Fajan's rule is important in explaining why some ionic compounds behave like covalent compounds in melting point, solubility, and conductivity. Next important long question is: to explain the structure and type of bonds in Diborane, BH. Diborane, BH structure and type of bonds. Diborane is an electron-deficient molecule, meaning it does not have enough electrons to form normal covalent bonds for all atoms. Structure: BH has 2 boron atoms and 6 hydrogen atoms. 4 hydrogens are terminal, each bonded normally to boron, BH sigma bonds. 2 hydrogens are bridging hydrogens, connecting the 2 boron atoms. Bond type: terminal BH bonds normal to electron covalent bonds. Bridging BH-B bonds 3 center to electron bonds, 2 electrons shared between 3 atoms. This is unique and gives Diborane its electron-deficient character. Shape: the molecule has a banana-shaped bond for bridging hydrogens. Overall, BH is tetrahedral around each boron. Tip to remember: Diborane is equal to 4 normal BH plus 2 bridging BH, B is equal to 6H total. Diborane's bonding is a classic example of 3 center to electron bonding in electron-deficient molecules. Next important short question is: 3. Explain the Lewis acid nature of boron trihalides. Lewis acid nature of boron trihalides, BX. Boron trihalides, like BF, BCl, BBr, are typical Lewis acids. Reason: boron has 3 valence electrons and forms 3 covalent bonds with halogens. After bonding, boron has only 6 electrons in its valence shell. It is electron deficient. According to Lewis theory, a Lewis acid is an electron pair acceptor. Boron can accept a lone pair from a donor, like NH, to complete its octet. Example: BF plus NH FbNH. BF accepts a lone pair from NH, forms an adduct. Tip to remember: boron trihalides are electron-deficient, love to accept electrons. Lewis acids. This property is important in catalysis and organic reactions, as BX can activate molecules by accepting electrons. Next important short question is: 4. What are silicones? Write their classification. Silicones. Silicones are synthetic polymers containing silicon, oxygen, CO, backbone with organic groups, like CH, attached to silicon. They are also called polysiloxanes. General formula: RCO, where R is equal to organic group, example CH. Properties: heat resistant, chemically stable, water repellent, flexible and elastic. Classification of silicones. 1. Straight chain, linear, silicones. Formula RCO. Example, dimethyl polysiloxane, used in lubricants. 2. Cyclic silicones. Formula RCO, ring structure. Example, hexamethylcyclotrisiloxane, used in making silicone resins. 3. Cross-linked, elastomeric, silicones. 3D network structure. Example, silicone rubber, used in seals, gaskets, cookware. Tip to remember. Silicones is equal to CO backbone plus organic groups linear, cyclic, or cross-linked. They are widely used in lubricants, cosmetics, sealants, and medical implants due to their stability and flexibility. Next important short question is: 5. Explain the structure of I and ICl ions. Polyhalide ions, I and ICl. 1. Triodide ion, I. Formed when iodide ion, I, reacts with iodine, I. Structure, linear I. Bonding, each I bond is slightly longer than normal I single bond due to electron delocalization. Electron arrangement, 5 lone pairs on terminal iodines, 3 on central iodine, giving linear shape. 2. Iodine chloride ion, ICl. Formed when iodine reacts with chloride ion. Structure, linear, ICl. Central iodine has 3 lone pairs, outer chlorines have 3 lone pairs each. Follows VSEPR theory, AXE linear geometry. Tip to remember. Both I and ICl is equal to linear shape, central atom with lone pairs, terminal atoms bonded. These ions are examples of polyhalides, important in halogen chemistry and redox reactions. Next important short question is: 6. Mention the classification of carbides with examples. Carbides. Carbides are compounds of carbon with a less electronegative element, usually a metal. They are widely used in industry for cutting tools, refractories, and steel production. Classification of carbides. 1. Ionic, salt-like, carbides. Formed with alkali or alkaline earth metals. Carbon exists as C, methanides, or C superscript 2, acetylides. Example, CaC reacts with water to give acetylene, CH. 2. Covalent, molecular, carbides. Formed with nonmetals or semimetals. Strong covalent bonding, hard and high melting. Example, SiC, silicon carbide, used in abrasives. 3. Interstitial, metallic, carbides. Formed with transition metals. Carbon atoms occupy interstitial spaces in metal lattice. Example, Fe, cementite, important in steel. Tip to remember. Carbides is equal to ionic, alkali, covalent, nonmetals, interstitial, transition metals. These types cover all industrial and chemical applications of carbides. Next important short question is: 7. What are pseudohalogens? Compare with halogens. Pseudohalogens. Pseudohalogens are molecules or ions that resemble halogens in their chemical behavior. They can form acids, salts, and interhalogen-like compounds, just like halogens F, Cl, Br, I. Examples: cyanogen, Cn, SCN, thiocyanate, N-azide. Comparison with halogens. Property halogens F, Cl, Br, I. Pseudohalogens Cn, SCN, N. Bonding diatomic molecules X, molecules or ions A or AX. Reactivity form acids HX, salts form acids, HCN, HSCN salts. Oxidation act as oxidizing agents can act similarly in some reactions. Interhalogen-like form interhalogen compounds can form pseudo-interhalogen compounds. Tip to remember. Pseudohalogens is equal to behave like halogens but contain C, N or S instead of halogen atom. Pseudohalogens are important in organic and inorganic synthesis, analytical chemistry, and formation of pseudosalts. Next Unit 1, Inorganic Chemistry. Long questions. First important long question is: explain the shapes of compounds based on VSEPR theory. VSEPR theory and shapes of compounds. VSEPR, valence shell electron pair repulsion, theory was proposed by Gillespie and Nyholm. It helps us predict the shapes of molecules based on the idea that electron pairs around the central atom repel each other and arrange themselves as far apart as possible. This includes bonding pairs, shared electrons, and lone pairs, non-bonding electrons. Steps to predict shape. 1. Find the central atom. 2. Count the valence electrons of the central atom. 3. Add electrons from bonded atoms, total valence electrons. 4. Draw Lewis structure and identify bonding and lone pairs. 5. Apply repulsion rules, lone pair, lone pair, lone pair, bonding pair, bonding pair, bonding pair. Common shapes with examples. Electron pairs shape example bond angle. 2 linear co 180 degrees. 3 trigonal planar BF 120 degrees. 4 tetrahedral CH 109.5 degrees. 3 bonding plus 1 lone pair trigonal pyramidal NH 107 degrees. 2 bonding plus 2 lone pairs bent HO 104.5 degrees. 5 trigonal bipyramidal PCL 90 degrees, 120 degrees. 4 bonding plus 1 lone pair seesaw SF less than 120 degrees, less than 90 degrees. 3 bonding plus 2 lone pairs T-shaped CLF less than 90 degrees. 2 bonding plus 3 lone pairs linear XCF 180 degrees. 6 octahedral SF 90 degrees. 5 bonding plus 1 lone pair square pyramidal BRF less than 90 degrees. 4 bonding plus 2 lone pairs square planar XCF 90 degrees. Tips to remember. Lone pairs push more reduce bond angles. Ax notation: A is equal to central atom, X is equal to bonded atoms, E is equal to lone pairs helps easily predict shape. Conclusion. VSEPR theory is simple, logical, and widely used in inorganic chemistry to explain molecular shapes, bond angles, and polarity. Visualizing molecules with lone pairs and bond pairs makes it easy to remember for exams. Next important long question is: 2. Draw the mode of N molecule. Calculate bond order, stability and magnetic properties. Molecular orbital energy diagram, mode of N. The molecular orbital theory, MOT, explains bonding by combining atomic orbitals to form molecular orbitals. Step 1. Total electrons in N. Each N atom has 7 electrons, total 14 electrons in N. Step 2. Molecular orbitals, sigma and pi. Order of orbitals for N, Z less than or equal to 8. Sigma 1s, sigma asterisk 1s, sigma 2s, sigma asterisk 2s, sigma to pz, pi to px is equal to pi to py, pi to px is equal to pi to py, sigma asterisk to pz asterisk asterisk. Step 3. Fill electrons in mode. Mo electrons. Sigma 1s 2. Sigma asterisk 1s 2. Sigma 2s 2. sigma asterisk 2s 2, sigma to pz 2, pi to px, pi to py 4. Total is equal to 14 electrons. Step 4. Bond order. Bond order is equal to electrons in bonding modes, electrons in antibonding modes 2 is equal to 10 to 4, 2 is equal to 3. Step 5. Stability. Bond order is equal to 3 triple bond very stable molecule. Step 6. Magnetic properties. All electrons are paired and is diamagnetic, not attracted to a magnetic field. Summary table. Property N. Electrons 14. Bond order 3. Type of bond triple bond 1 sigma plus 2 pi. Stability high. Magnetic property diamagnetic. Tip to remember. Bond order is equal to 3 triple bond strong and diamagnetic. N is very stable and unreactive, making it a major component of air. Conclusion. Mo theory clearly explains why N is stable, has a triple bond, and is diamagnetic. Drawing the mode helps visualize bonding and antibonding electrons, making it easy to calculate bond order and predict properties. Next important long question is 3. Draw the mode of co-molecule. Explain bond order and stability. Molecular orbital energy diagram, mode of co. Step 1. Total electrons in co. Carbon, C, has 6 electrons, oxygen, O, has 8 electrons, total 14 electrons. Step 2. Molecular orbitals, sigma and pi. For diatomic molecules with Z less than or equal to 8, the Mo order is sigma 1s, sigma 1s, sigma 2s, sigma 2s, sigma to pz, pi to px is equal to pi to py, pi to px is equal to pi to py, sigma to pz. Step 3. Fill electrons in mode. Mo electrons. Sigma 1s 2. Sigma 1s 2. Sigma 2s 2. Sigma 2s 2. Sigma to pz 2. Pi to px, pi to py 4. Total is equal to 14 electrons. Step 4. Bond order. Bond order is equal to electrons in bonding modes, electrons in antibonding modes 2 is equal to 10 to 4, 2 is equal to 3. Bond order is equal to 3 triple bond. Structure 1 sigma bond plus 2 pi bonds. Co is very stable due to high bond order and strong triple bond. Step 5. Stability and polarity. Co is diamagnetic, all electrons paired. Slight polarity exists because oxygen is more electronegative. C has slight positive charge, O slight negative charge. Summary table. Property Co. Electrons 14. Bond order 3. Type of bond triple bond 1 sigma plus 2 pi. Stability very high. Magnetic property diamagnetic. Tip to remember. Bond order is equal to 3 triple bond strong and stable molecule. Conclusion. Mo theory explains why Co is stable, has a triple bond, and is diamagnetic. Drawing the mode helps visualize bonding and antibonding electrons, making it easy to calculate bond order and predict molecular properties. Next important long question is 4. Explain the structure, bonding and preparation of diborane. Diborane, BH structure, bonding and preparation. 1. Structure. Diborane is an electron-deficient molecule, meaning it does not have enough electrons to form normal covalent bonds for all atoms. Formula: BH to boron atoms and 6 hydrogen atoms. Hydrogen atoms. 4 terminal H atoms bonded normally to boron, BH sigma bonds. 2 bridging H atoms connect both boron atoms. Shape banana-shaped B bridges. Bond angles, ~120° between terminal H and B, ~97° between bridging H and B. 2. Bonding. Terminal B-H bonds normal to electron covalent bonds. Bridging B-H-B bonds 3 center to electron bonds, 2 electrons shared among 3 atoms. Electron deficient nature. Boron has only 6 valence electrons in normal bonding explains unusual bonding. 3. Preparation of diborane. Method 1. Reduction of boron trifluoride, BF, with lithium aluminium hydride, Lyl. 4 BF3 plus 3 Lyl 4 to B2H6 plus 3 LiF plus 3 AlF3. Method 2. Action of sodium hydride, Na, on boron halides. To BCl3 plus 6 Na B2H6 plus 6 NaCl. Tip to remember. Diborane is equal to 4 normal BH plus to bridging BH, B is equal to 6H total. Think of banana bonds bridging to borons. Uses. Rocket fuel, high energy content. Reducing agent in organic chemistry. Conclusion. Diborane is a classic example of electron-deficient bonding with 3 center-to-electron bonds. Its unique structure, bonding, and preparation make it an important molecule in inorganic and industrial chemistry, and drawing its structure clearly helps in remembering it for exams. Next important long question is 5. Write preparation, structure and properties of Borazine, inorganic benzene. Borazine, inorganic benzene preparation, structure and properties. 1. Introduction. Borazine is called inorganic benzene because its structure is similar to benzene, CH, but B and N atoms replace C atoms alternately. Formula BNH. 2. Preparation. Method 1. From boron trichloride, BCl, and ammonia, NH. 3 BCl3 plus 6 NH 3B3 N3H6 plus 9 HCl. Method 2. From diborane, BH, and ammonia. 3B2H6 plus 6 NH3 to B3 N3H6 plus 6H2. Tip to remember, Borazine is made by reacting boron compounds with ammonia. 3. Structure. Borazine has a planar hexagonal ring like benzene. Alternate B and N atoms form the ring. Bond lengths, B-N bonds are equal. ~1.45a shows partial double bond character, resonance. Each B has 1 hydrogen, each N has 1 hydrogen. Resonance makes the molecule stable and aromatic-like, though less than benzene. 4. Properties. Physical, colorless liquid, low melting and boiling points. Chemical. Less reactive than diborane. Can undergo electrophilic substitution similar to benzene, but weaker due to B-N polarity. Hydrolysis, reacts slowly with water, produces boric acid and ammonia. Aromatic character, due to delocalized electrons in the B-N ring. Tip to remember. Borazine is equal to BNH, hexagonal ring, alternating B and N, like inorganic benzene. Conclusion. Borazine is a key example of a boron-nitrogen compound. Its planar, resonance-stabilized structure and unique properties make it important in inorganic chemistry, materials science, and high-temperature polymers. Drawing its hexagonal ring with alternating B and N atoms helps easily remember its structure for exams. Next important long question is 6. Structure, bonding and reactivity of xenon compounds, oxides, halides, oxyhalides. Xenon compounds, structure, bonding, and reactivity. 1. Introduction. Xenon, Xe, is a noble gas, generally inert, but forms compounds with highly electronegative elements like oxygen and fluorine. These compounds are stable under normal conditions but reactive in strong oxidizing environments. 2. Xenon oxides. Examples: XeO, xenon trioxide, XeO, xenon tetroxide. Structure: XeO trigonal pyramidal AXE, XeO tetrahedral AX. Bonding: covalent with XeO, multiple bonding. Reactivity: XeO is explosive and a strong oxidizing agent. XeO is very unstable, decomposes easily. 3. Xenon halides. Examples: XeF, XeF, XeF. Structure and geometry: XeF linear AXE, XeF square planar AXE, XeF distorted octahedral AXE. Bonding: covalent bonds with coordinate contributions from Xe lone pairs. Reactivity: highly reactive with water, forms xenon oxides and hydrofluoric acid. Used in fluorination reactions in organic chemistry. 4. Xenon oxyhalides. Examples: XeOF, XeOF. Structure: derived from XeF and XeO bonding. Bonding: covalent with Xe central atom using lone pairs for geometry. Reactivity: oxidizing agents react with water to give acidic solutions. Useful in synthesis of fluorinated compounds. Tip to remember: Xe compounds is equal to Xe forms covalent bonds with O or F shapes depend on lone pairs, highly reactive oxidizers. Conclusion: xenon forms oxides, halides, and oxyhalides due to its ability to use d orbitals and lone pairs. Shapes are explained by VSEPR theory. Their high reactivity makes them important in inorganic synthesis and fluorination reactions.